All right, here we have an example on kinematics of rigid bodies. We have an old school car engine. It's a crank slider crank mechanism. The crankshaft is rotating about this center O, and it pushes the connecting rod, and the connecting rod pushes the piston into the engine body. So we know we have a constant angular velocity of 200 radians per second on the crankshaft. We have some dimensions of the crankshaft. We want to know, after 1 second, starting from this theta equal 30 degrees, what is the crankshaft angle after 1 second? And also we want to know at this instant what is the velocity and acceleration of point P. So let's gather all our information in a nice, logical, and cohesive way. So what do we have? We know all the geometries. So we know that the distance from O to P is 0.1 meter. But I'm going to write it as a vector because it is going to help me down the road. So R is 0.1 cosine of 30 degrees at this instant. 30 degrees. I plus 0.1 sine 30 J in meters. Because part of the problem, the first part, is about a transition, rotation from some initial angle to final angle. Let me do that. I want to write it as two separate states. State 1. We know we are at angle 30 degrees, theta 1. And our omega is 200 radians per second. My state 2 that I need to find, I want to find this theta 2 that I don't know. Omega remains the same. Omega is constant. Omega 2 is always that 200 radians per second. And in fact, the transition between these two is governed by acceleration, or let's call it alpha is 0, or omega is constant. So that's a good information to have. What I wanted to do to be more systematic, let's make this as a sub part of state 1 because now everything is more logically organized. I don't care. Likely I don't need to know the R2 and the state 2 because nobody's asking about that. What else do I know? I think that's all. And I need to find theta 2. And the problem is asking about velocity and acceleration. So V of P, because these are in general vectors, so let's not assume that we want to find magnitude, and acceleration of point P. So let's get to the solution. Let's stick with part 1. In a rotational system, when we're dealing with angles, angular velocities, and so on, all our equation is basically the same as a rectilinear motion. We are dealing with first and second derivatives of a quantity. In that case, that quantity is angle. because acceleration is constant, we can deduce that my theta, well, let's do it this way. Oh no, acceleration is 0. Sorry, acceleration is 0. My omega remains constant, always 200 radians per second. And if omega is constant, I can write my change of angle, theta 2 is theta 1 plus this omega t, the time that has passed. Oh, one other thing. I realized I could have done this better. So this is when I start my stopwatch. At this state, I know time is 1 second. I missed that part. So omega t, all good. So let's put numbers. I have theta 2 is 30 degrees at the beginning, plus, well, I have to convert everything to same set of units. My omega is radians per second. So this is radians per second, which I can write as every pi radian is 180 degrees. So that gives me, is my cancel, I can get degrees per second times 1. And I have already done the math. Let me find it. This will turn out to be 11,489 degrees. So the angle is that much. Maybe this doesn't help us a lot. I can write it as this becomes 31 full turns. 31 times 360 degrees. And the leftover will be 329 degrees. So basically the angle will be, this one will rotate a lot. I'll be roughly here when the total angle, well, this angle from the original horizontal line is 329. So let me delete these, I don't like them. Okay, so that is part 1. About part 2, I need to find velocity of point P when theta is 30 degrees. So at that state 1, I know Vp in a very nice compact form. I can write it as omega cross r in vector form. And to help me, I kind of implicitly did this, but let me be more explicit. I am taking this as my x, this one as my y, and z is coming out of the page. Because omega, using right hand rule, omega vector is into the page, so that one is 200 but in minus k direction, cross my r, 0.1, let's call this r1, cosine 30i, 0.1 sine 30j. I can distribute the cross product. I have 200 minus 200 times 0.1 times k cross I, minus 200 times 0.1 k cross j. And I never remember. I always do this. This is the direction of positive cross products. So K cross I gives me positive J. These are arrows. Arrow, arrow, arrow. So this becomes minus 20. K cross I is J. Minus 20. K cross J. I go the opposite direction. I go that way. So I have minus I. And this might, oops, where were the sines and cosines? They disappeared. Wait a second. So 20.1 cosine 30 K cross I minus 200 times 0.1 times sine 30 K cross J. Okay, now I have 20 cosine 30 J, and the minus with that minus cancels. This becomes positive 20 sine 30 I, and all of these is 17.3. Which one is my I? 10. No, 10 I minus 17.3 J meters per second. So my velocity, as I expect, has positive I component and negative J component. So something like this, which I know has to be perpendicular to the line OP. So that is velocity, finally acceleration of P. I know it is alpha cross R minus omega square scalar R, basically the radial and transverse or centripetal directions. I know alpha is 0 here, so this one disappears. All I have is minus omega squared R, which is R1, and that is minus 200 squared, and my R was 0.1 cosine 30 I plus 0.1 sine 30 J. And if you do all the numbers, you will get minus 3,464 I minus 2,000 J meter per second square. So as we expect, the direction is just in the opposite direction of line OP or R, and that is my acceleration. Okay, so here is just a quick rundown of some of the concepts we have seen, and I will leave it here.